The transmission of water waves can be demonstrated in a water ripple tank. Here's an example of a ripple tank we could use. The wooden plank here bobs up and down periodically to disturb the water's surface and create water waves. We can analyse the water waves by hanging a light above the tank and watching the shadows below. On the other side of the tank, we've split the water into two sections. For this section, we have the same deep water that the plank is creating waves in. But up here, we've raised the bottom of the tank so we have shallower water. Let's look at what we'd see in the ripple tank in more detail. Here's a simple diagram looking into the tank from above. We can draw lines to represent the shadows under the tank, which correspond to the peaks of the water waves. Remember that transmission is when a wave passes from one medium to another. We can consider the deep water and this section of shallow water as two different media. This is because there's less water to be displaced by the wave, which changes the properties of the wave here. Since we've set up the tank so this change in depth is sudden, we've created a clear boundary here where transmission will occur. So what will the waves look like after this transmission? Well, the waves in the shallow water will have a shorter wavelength. Remember that wavelength is a distance between two equivalent points on the wave, such as two peaks. In this case, the wavelength would be the distance between two shadows in the ripple tank. We can see the shadows in the shallow water will be closer together than in the deep water, though you don't need to know why this happens at GCSE. But you should be able to recognise that this shows us that the wavelength here is shorter. But what about the frequency? All the water waves will have the same frequency. Remember that frequency is the rate at which the cycle of a wave repeats, or the rate at which the waves are created. Imagine we're watching these waves move along the ripple tank. Notice that these shadows are parallel to the boundary that we've created here with the shallow water. It's also parallel to the opening for this section of deep water here. So when a shadow hits this boundary, we'll see a shadow start moving in the top section at the same time a shadow starts moving in the bottom section. One way of thinking about this is that we're creating two new smaller waves when the original wave is split. So these two new waves are created at the same time. Furthermore, they're created at the same rate that the original waves in the ripple tank are made, so they must have the same frequency. So what does this tell us about the speed of these waves? Well, this means that the waves in the shallow water will also have a smaller wave speed. Remember that wave speed is the speed at which the waves travel. In this case, the speed the shadows move. We can calculate wave speed by multiplying the wavelength of a wave by its frequency. In this case, we've just shown that the waves in the shallow water have a shorter wavelength but the same frequency. This means that the shallow water waves must be travelling slower than the waves in the deep water. The transmission across the boundary has caused the wavelength and the speed to change, but not the frequency. Now, you won't be expected to recall this demonstration in an exam, but you need to be able to explain what happens to the wavelength, the frequency, and the speed during transmission, and not just for water waves. These effects can also be seen in other boundaries. Let's suppose we have a boundary with air on one side and glass on the other. First, let's suppose we have a transverse light wave travelling from the air into the glass. Transmission occurs, causing the wavelength of the light to decrease. We could also have a longitudinal sound wave approaching the boundary in the same way. Again, transmission occurs, causing the wavelength to decrease. In both of these cases, the frequency of the waves has not been affected. So we can deduce that the waves were travelling fast in the air, but the transmission has caused them to slow down in the glass. For your exam, make sure you understand and can explain what's happening here, especially for sound waves.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!